Okay, while you're...
Do you want me to write on the board the picture, or should they just go down?
They better have it by now.
What?
No.
So
They better have it by now.
Okay.
Okay, fold correctly, put your heading on correctly, give Jerome a nice clean left edge. If you don't do all of those things, you may get points deducted. Okay, so do that right. While you're doing that, let's talk about this week. So Wednesday's homework, that's old news. Exam 2. All right, so how do you study? There's the review outline, and then let the review outline kind of point you at the applicable web work, written homework, recitation quizzes, lecture videos, okay? So the centerpiece of your studying is that bullet point list. That will help you, guide you to what web work you should be looking at, what written homework, etc. Okay? So let me show you that in exam prep. This folder here, exam 2. Hopefully you've already been here. Concepts and skills. Now, please note these important notes. So, in Module 5, you are responsible for the covariation stuff we did with comparing the changes, right? So, bottle problems, the walk problem that we did, that's listed on the outline. Okay? Also, what we did last time on Monday, the arrow example and your web work that was due today, that you're responsible for that, and that's not on the outline. Okay? But then there's also at the end of the outline, it talks about all the stuff about polynomials. You're not responsible for that. We didn't cover that. Okay? So if what I just explained was unclear, just read this carefully. It explains that. So you know exactly what's on the exam. Okay, then I've posted the 2 quizzes on exponential growth, Module 4, a blank version and solution versions for both of those. And those are the 2 quizzes that pertain to this exam. Okay, so most of the exam is Module 4, exponential growth, but there is a considerable, there's the whole stuff on, for Module 3, average rate of change, using function notation to represent average rate of change, and what does that number mean? And then what we've done in Module 5, bottle problems, walk problems in terms of analyzing the changes, and how does that play out graphically, and then analyzing the graph, analyzing graphs like the arrow problem on Monday. Okay, so that's for some of you, it's Friday, the exam. For some of you, it's Monday. Any questions about the exam? So make sure so I've got a summary on the announcements, and then you've got the exam prep area. And then also, what often happens is students take tests and they don't do as well as they hoped, and then they come and they look over their exam, and then that's when all the learning occurs. We have these rich conversations about problems on the exam, and I always say to the students, we just needed to have this conversation a week earlier, and then you would have gotten a letter and a half grade better. Okay? So, figure out what you don't understand, and get to Jerome, get to me, and let's have these conversations where you really consolidate the material before the exam, not after. Okay? So find us. Or find someone in the Pathways Tutor Center. But don't trick yourself into thinking you get it. Okay? So everything seems crystal clear in class, but it fades, right? And you have to remember it all and really understand it so you can succeed on the test. So find Jerome, find myself, figure out what you still need help with, and get the help you need before the exam. Any questions? Okay, so we're going to move on to Module 7, which is trig. We're going to spend most of the rest of the semester talking about trig. And those who have had trig before, erase your memory banks. We're going to approach this from a very different point of view, and we're going to bring lots of meaning to it. And so I think most people who have had trig and then experienced this really appreciate it because it's like, oh, this all makes sense. Why are we doing all this? Okay? So I think you will enjoy it. It's my favorite part of the course as well. So trig begins with understanding angle. Angles and angle measure. Okay, so that's where we're going to start Module 7. This is not material for Exam 2. Okay, so this is for Exam 3. So first of all, we better know what an angle is. What is an angle? An angle, it consists of two rays with the same endpoint. And that endpoint is called the vertex. Okay, so here's examples of angles. Two rays, which are lines that start in an endpoint and then extend forever. And if those two rays have the same endpoint, it forms an angle. What does it mean for two angles to have the same measure? What does it mean for two angles to have the same measure? Anyone want to give a shot at this? What's that? Equal sides. Like who said that? Like the lengths, or what do you mean by equal sides? The length of the sides are equal?
Yeah.
So if the lengths of the sides are equal, then the angles have equal measure. Danny?
Both angles are the same distance apart from one another?
You mean the segment, the lines?
The line segments.
So the lines, the rays are the same distance apart. The rays are the same distance apart. Okay, so how about this? So what's the distance apart from here? So here's the distance that they're apart, right? And then here's a distance from here to here. So since that distance is greater than this one, this has a larger measure than this one. Yes? So there's something that doesn't work with the distance apart, okay? Distance apart. So actually, before we answer this question, we really have to answer, we have another question to answer first, and that is, what is it that we're measuring when we measure an angle? What is it about the angle that we're measuring?
Fraction of a circle.
Fraction of a circle, okay? Other possibilities. What are we measuring? So the angle itself has nothing, there's no circle involved in the angle itself. So if we just have an angle, what attribute of the angle are we assigning a value to? So what attribute of this two rays, so remember we talked about objects, and objects have attributes, measurable attributes or quantities. So think of this angle as an object. What attribute of this object, this angle, are we assigning a value to? Yeah. What's that? The vertex. So what about the vertex? The vertex is another object. What attribute about an angle are we assigning a value to? Anybody? Distance the rays are apart? What's that? All right, so Walter remembers. Okay? How open it is. We think of that angle as like a door, right? So you have the threshold of the door, and then there's one ray, and then the door is the other ray. We're really measuring how open the angle is. So that's what it's a measure of. So in terms of order these angles from least to greatest openness. Least to greatest openness. I'm sure you can do it in 20 seconds. Go. So least to greatest openness. Talk to the person next to you. Chad, which has the least openness?
C.
He wants C. C. Michaela, you agree with that? You don't think C has the least openness? Which one do you think has the least openness? B has the least openness. Dissension. Lexi, what do you think? C has the least openness. So if you think about a door, so like if it's closed, that's like 0 openness. So as we open the door, then which one would come first? Yeah, so C would have the least, and then B would have the greatest openness. So we go C is the least, then A, then B has the greatest amount of openness. So now we ask the question, how do we assign an actual value to the openness of an angle? Or in other words, what's the basis for measuring angles? How do we assign an actual value of openness? So let's investigate that. So you're going to figure that out. So we're going to design a pizza cutter. So here's 2 different versions, but you see the angle formed there, the vertex at the center of the pizza. And so we want to design a pizza cutter that will cut the pizza into 9 equally sized wedges. Okay? So we want to design a blueprint for this pizza cutter. But you don't have a protractor. Okay? So a protractor, that assumes that we already know how to measure an angle. So we're starting from scratch here. We don't know. We're trying to figure out how we're going to get a measure or a value on the amount of openness. So, but you do have like common just desk supplies: pencil, ruler, tape, scissors, string, anything like that is fair game. But you don't have something for measuring angles, because that's what we're figuring that out. We're trying to come up with a way to measure an angle, measure an angle. So, how would you do this? How would you get, say, this one right here? So here you see this angle forming right here, and we need this to cut. We need that to cut 1/9 of the pizza, right? So we want 9 equally sized wedges. That would be that, and 9 more would make the pizza. So how would you create a blueprint for that using just desk supplies, pencil, ruler, tape, scissors? Okay, so work with someone else. Get 3 or 4 minutes. Come up with a way to devise how that will cut exactly the pizza into 9 equal pieces. Is the task clear? Does it make sense? This is actually in Module 7, Investigation 1. Something similar to this. What page is that on? What's the problem that's saying design pizza? Does it say 9 equal pieces? Does it say 9 equal pieces? Number 2 on 269? On 259. Page 259, number 2, is this same task, okay? It's the same task. So work together. I will be calling on several of you to see what you came up with. I'm going to take attendance. Okay, let's see. This Sean here. How'd it go? Okay, so he said he took a string and made a circle around. So let me kind of try to draw this. Oh, I had pizzas to show you. Come on. Here we go. Does that make you hungry? Okay, then how about that one? I don't want you to be hungry, so we can work on that one. All right. Okay. So you wrap the string around. Lost it. Come on. All right, good enough. Okay, and then? What'd you say? Okay, so then we're gonna have some two ends to it, and then what? Okay. So he's going to extend that string out. So now you got that length of string that you just wrapped around the circle.
And then, let's say it's like 36 inches.
Okay.
Divide that by 9, so you get every.
So use your ruler to divide it up into 9 equal segments. See if I can do that. Is that 9? It's a little bit longer here. Okay. What'd you say? Okay, so he's marking these points on the string, and then he's going to wrap it back on the pizza, and so then the circumference of the pizza then will be broken up into 9 equal pieces. Let's see how I do. So you do 9? Is it 10? 1, 2, 3. Oh, look at that. All right, so you do that string up into 9 equal pieces, and then join those to the center. Does it work? Does what he did work? Okay, so this is giving us our. Anyone have a different idea? So I don't want to. How many people came up with this idea? Good, more than half. All right, so yeah, this was kind of the intention, that you would wrap a string around, break that string up into 9 equal lengths, wrap it back around, and that will be how we can wedge off this pizza so that they're all equal size pieces. And this is what Elon said before. He said that it has to do with a fraction of the circle. All right. So really, the basis of measuring angles has to do with what? Where does the basis for measuring angles come from? It has to. So the whole point was that we wrap this string around a circle, and the length of that string was its circumference. So an angle then has what to do with circumference? You said it before. Eric, what does the angle have to do with circumference?
That would be just the two rays for the 2 rays from the circumference goes in the middle of the pizza, so that's what has to do with the circumference.
Okay, but what are we doing with the circumference to define this angle that we're going to call 1/9?
Divided by 9.
Yeah, so we're taking a fraction of the circumference. So angle measure is about taking a fraction or percent of the circumference. That gives us an amount of openness, right? Because when you open a door, it's like you're rotating around a circle. So the fraction of the circle that you rotate, or that the percent of a circle that you open, then forms our basis for angle. So we're going to call this, the measure of this angle, 1/9. Angle measure. Why? Because it's the amount of openness that corresponds to 1/9 of a full circle or full rotation. So that angle, that amount of openness right there, that amount of openness, we'll start by saying that's a 1/9 angle. That's how we'll measure it, because it's 1/9 of the circumference, or 1/9 of a full rotation. So the measure of an angle is based upon the percent or fraction of a full circular rotation. Another way to say that is, it's the circular arc length. How much arc length we cover relative to the whole circumference. So these are two different ways to say the same thing. So how much arc length is measured off with respect to or relative to a full circumference. And this is what we can measure openness, the openness of the angle. Okay, so then what is this angle right here? It's not 90. It's not 90. What is this angle right here? Based on what we're saying. 1. So you think of a circle, you put the vertex at the center of the circle, and what question do we ask? We ask, what fraction of a circumference do the rays, the openness of the rays, are what fraction of a circumference? 1/4 or 25%. Okay? 1/4 or 25%. Okay, here's another angle. What about this? 1/3? No, that's not the angle I'm seeing. This is what I want. This one here. This is the way I've shown with the blue arc there. This would be a 2/3 angle. 2/3. 2/3 of a circle. The openness corresponding to 2/3 of a rotation. Or arc length, right? So this arc length is, from here, this arc length around here is 2/3 of the whole circumference. Okay? This angle here. This is the 1/6 angle. This is a 1/6 angle. Okay, does it make sense? Anybody have a question? Okay, so then therefore, what are in light of this, what are degrees? What are degrees? What does an angle of 1 degree represent? What is 1 degree? What does it mean? Eric wants to try. 1 over 360. So it's an amount of openness that corresponds to. So here's like 1 degree. Okay. We can zoom in on that. So what amount of openness is that? Yeah, so it's what he said. 1/360th of the circumference is cut off by the angle's rays. So we think about what fraction of the circumference is cut off by the rays of the angle. Okay, and so this is this word subtend. So an angle with measure 1 degree, whose vertex is placed at the center of a circle, has rays that subtend an arc length that's 1/360th of the circumference. So subtend just simply means to cut out a piece. Subtend, so the rays subtend or cut a piece of the circumference. The fraction that piece is of the whole circumference then is the measure of the angle. So the rays cut out an arc from the whole circumference, or they subtend an arc length. So this subtend word is something that you use in pathways a lot, so I want to make sure when you see that, subtend is the rays subtend a piece of arc length. The rays cut off a piece of arc length. Okay, so then look on page. There's just a couple quick exercises there. You can ask, what is an angle of, so 36 degrees. So can you articulate exactly what an angle of 36 degrees is? So, is that? Yeah, number 4 on the next page. What it means for an angle to have a measure of, they have 10 degrees and 47 degrees. So practice talking that out with the person next to you. What does it mean for an angle to have a measure of 10 degrees, part B, and 47 degrees, part C? Next page. Top of the next page. Just turn the page. Okay, half the class should be talking right now. You're working on articulating this precisely. Okay? Being able to explain it in all detail means that you really understand it. Okay? So half the class is talking, then you switch, the other class is talking. Practice what these mean. Okay, this Sean back here. What is a 10-degree angle? What does it mean if an angle has a measure of 10 degrees? What? So a 36 of the circle. Well, it has to do with a 36 of the circle. We want to be more precise about it. So what does it have to do with a 36th of the circle? The area of the circle. Alex, what do you think? What's a 36-degree angle? Is that what I asked? 36? Yeah, what's a 36-degree angle? Or did I say, is it 10? 10, sorry. What's a 10-degree angle? Sorry. Okay, it has to do with 1/36 of the circle, but it is not 1/36 of the circle. Sorry, Walden?
It has rays that's sub 10, the arc length that is 1/36.
Exactly. Right. Yeah, so you just replace it here. It has rays. The angle whose rays sub 10 in arc length, that's 1/36 of the circumference. That's what it means. It doesn't mean 1/36 of a circle. It means that the angle itself, its rays cut off an arc length, and that arc length is 1/36 of the circumference. Okay? So then, what about 180-degree angle? 180-degree angle. Aiden, what would a 180-degree angle mean?
It's rays sub 10 circle to create one pair in arc length of 1/2 of the circumference.
Yeah, so the rays cut off, so that's called a straight angle. If the rays cut off, can't do it. Can't quite do it. So if the rays cut off 1/2 of the circle's circumference. Okay. So that's what degrees are about. So in the beginning, so when we had circles, there's not something inherent about that a circle matches up with 360. The Babylonians picked that. They picked 360. Now there's a reason they picked 360. Does anyone know why they picked 360? What's that? Yeah, so they figured out that 1 year was about 360 days. And so they thought it was. And 360 has lots and lots of factors, right? You can divide by 2, 3, 4, 5, 6, 8, I think, 10, 12. Okay, so it divides, lots of numbers divide it evenly. And they were estimating that a year was 365 days long, and that's the time that Earth circles the sun. So that's why they picked 360. But there's nothing about a circle that intrinsically, you'd pick the number 360. You can pick 400, you can pick 100. So 360 was a man-made choice, okay? A man-made choice. And so when you think of degrees now, you think of them as cutting off some percent or fraction of the circular arc length if you broke the arc length up into 360 equal pieces. Okay. So let's look at something else here. As my daughter says, something else. She always wants to do something else. Something else. Okay. It's just that stage. So what am I showing you right here? So in the back, can you see 3 circles? Do they show up dark enough back there? I got a couple nods. Okay. All right, so, and maybe you can't see though, so the scales on the axes are even whole numbers, okay? Not even, they're whole numbers. 1, 2, 3, 4, 5, 6. Okay, ready. So I'm going to add an element to this picture. Do you see that right there? So I added a purple segment. What did I just show you with that purple segment? What am I representing? An angle? Am I representing an angle? Maybe if they're the same ray, right? That'd be a 0 angle. If those were 2 rays on top of each other, it'd be like a 0 angle. But I'm really showing what? The radius, right? The radius of the smallest circle, so that radius is 1. Now, keep your eye on that radius. Watch. So I'm going to take that radius. That's its normal place, right? From the center out to the edge of the circle. But I'm going to take it, I'm going to peel it off, its normal place, and I'm going to put it on the circle itself, maintaining that radius length. So this is a powerful image to understand what we're about to talk about. So fix it in your mind. Take it from its normal spot, pull it off, wrap it on the circle. So it still has one radius length. It's now just arced. It's just wrapped on the circle. Okay? What am I showing you here? Oh, I jumped the gun. Right there. What's that? Radius of? Second circle, which is? 4. Okay? Same thing. I'm going to take that from its normal place, pull it off, maintain its length, and wrap it on the circle. One more time. What am I showing you? Radius for largest circle, which is 6. Watch it. Don't forget it. I'm going to take that radius. I'm going to wrap it on its circle. So now you have 3 arc lengths. I want you to talk for a minute. And I want you to say, as many ways as you can think of, what is different about the 3 arc lengths? And what is the same? As many things as you can think of that make those. Okay, so color is off the table. Okay, of course, colors are different. I'm talking about as objects in this image, thinking mathematically, what is different about, as many things that you can think of that's different about those 3 arc lengths, and what's the same about those 3 arc lengths. Okay, go. Okay, Wyatt. How about something that's different about those three arc lengths? Their actual length. Is their actual length different? Yeah, the first one was, we got 1, 4, and 6, right? Anything else that's different? That's big. Yeah, Alex.
The rays that extend to the circumference are like different sizes.
Oh, so they're distance away from the center, kind of? Yeah, so how far away they are. So, and actually, how far it is away is the same as what? Is the same as the length of the arc, right? Because this arc length is 1, and it came from this circle of radius 1. So this arc is 1 away, this arc is 4 away, and its length is 4. This arc is 6 away, and its length is 6. Is that what you were saying? Like how far away it is from the center? Yeah, okay. Anything else that's different? Okay, what's the same about those three? Matt? Is there anything that's the same about those three? Okay, cool. So all of them, so in their actual lengths as the scale on the axes, they're different, 1, 4, and 6. But all of them are 1 radius length, right? So it doesn't matter that we chose different size circles but all of them are still 1 radius length of its respective circle. That's good. So they're all 1 radius length. What else is the same? Michaela? They form the same angle. And because angle comes from what? Okay, why do they form the same angle? Why do they form the same angle? Yeah, Adam.
Their rays subtend the same portion of the circumference radius.
Right. So if I was to come along here and say, here's this what we call the terminal side. So the positive x-axis there, see that? That's kind of like our starting point for this openness of this angle. So we call that the initial side of the angle. Okay? And the language we use is, this initial side is the 3 o'clock position on the circle. So if you think about the circle as a clock, they often use this language. This is the 3 o'clock position. Pointing straight to the right from the center is the 3 o'clock position, or also the positive x-axis. You could say positive x-axis. So the positive x-axis, or this 3 o'clock position, forms the initial side of the angle, and then what Adam said is, or Michaela and Adam said that all 3 arcs then mark off kind of the same So if you imagine opening up that angle from the 3 o'clock position right to there, then this is called the terminal side of the angle. Terminal meaning the end. And to open up this angle, we're sweeping which way? Clockwise or counterclockwise? So we're sweeping. All this language is really important. We're going to use it for the rest of the course. Sweeping counterclockwise. Okay, so our initial side is the 3 o'clock position, the x-axis. We're going to sweep counterclockwise to form an angle, and then where we stop is the terminal side. So they said that all 3 of these arcs then form the same angle. All those arc lengths terminate along a line, which is our terminal side of the angle. So each of those is the same. Each of those is the same fraction of its circumference, right? If the same angle cuts out all three of those arcs, then they must all be the same fraction of their own circumference. So, is radius length a valid way to measure angles? Is radius length a valid way to measure angles? Yeah, because it will always give you the same amount of openness. If you take a radius and lay it on its respective circle, you always get the same amount of openness. We could do it for 2, we could do it for 3, we could do it for 10, we could do it for 100 or 1,000,000. And laying that radius on its circle would result in define the same angle, the same amount of openness. Okay, so degrees was one way, right? Degrees is based on 360 equal parts of the circle. So this is another way to measure angles based on radius length. So the angle whose rays cut off, don't pack up and stop paying attention. Okay, the angle whose rays cut off one radius length. So instead of saying we're going to cut off a fraction of the circle, now we're going to say how many radius lengths does it cut off? Because we're seeing that's a valid way to do it. So this is one radius length. No matter which circle you choose, one radius length. Okay? And so then we call that angle that cuts off one radius length of arc length, who knows? 1 radian. That's what a radian is. It's about what arc length is cut off. 1 radian, then, is an angle with a measure of 1 radian, has rays that cut off 1 radius length, no matter what circle you're looking at. So now I'm going to show you. So if we go further, we go up to now I'm showing you 2 radius lengths on all the circles. So what's the measure of that angle in radians? 2 radians is the angle whose rays cut off 2 radius lengths. All those arcs are a length of 3 radius lengths. Okay, all of those are 3 radius lengths. Therefore, the angle is 3 radians. So here is 3 radians. So then what is halfway around the circle?
5 radians.
Something a little bit more than 3. Right? Something closer to 3 than 4. Pi, right? Okay, so this is what the number pi means. It's how many radius lengths it takes to go exactly halfway around the circle. And so that's why this 180-degree angle measured in radius lengths halfway around the circle ends up being pi radius lengths or pi radians of openness. Okay. Start studying for your exam if you haven't yet. Yeah, John.